Hello and welcome to today's webinar presented by Dlubal Software. Today we're working in our finite element analysis and design software, RFEM. The topic for today's webinar is ASCE 7 2016 Response Spectrum Analysis in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Stefan Frenzel will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the content for the next hour today, I want to give a brief introduction to our dynamic add-on modules that work within our main program, RFEM. Then we'll move on to our example today where we will run a natural frequency analysis. Here we'll consider different mass cases as well as how to combine these into mass combinations. We'll run a natural vibration calculation where eventually we'll determine the frequencies, mode shapes, and mass participation factors of our structure. Then we'll move on to a response spectrum analysis. This will be per the ASCE 7 2016 today, but I just want to make a note that the NBC 2015 is also available as well as many other international standards. So today's webinar, 95% can be used relevant to any standard. We also will take a look at the response spectrum analysis calculation options and eventually determine our results, where we want to focus at the end on elements such as story drift, story shear, and p-delta considerations. So regarding the dynamic add-on modules in RFEM, we have a total of 4. So within the main program RFEM, we want to initially begin by modeling our entire structure. We can load the structure and we can run a full static analysis. But the minute that we want to run any type of dynamic analysis, this does require the add-on modules. The first is called RF-DYNAM Pro Natural Vibrations, and this is a prerequisite to the rest of our dynamic add-on modules. You have to determine what the natural frequencies and mode shapes are of the structure. Our second add-on module is RF-DYNAM Pro Force Vibration. So this allows us to run a linear time history analysis. Now we also have the ability in this module to run a multimodal and multi-point response spectrum analysis. This includes all of the standards such as the ASCE 7 and the NBC standard. The difference here though with this module in comparison to what we'll be using today, it's a little bit more limited. We can't export out the equivalent loads. It doesn't include things like accidental torsion. But it is possible for a little bit of a slimmed down response spectrum analysis. The third add-on module is actually a module extension to force vibrations. This is RF-DYNAM Pro Nonlinear Time History. So this just releases a couple of nonlinear solvers for the time history analysis. Now, as far as these 2 modules here, I previously did a couple of webinars available on our YouTube channel that really explores the depths of these modules. Today we won't be getting into them at all. Rather, we'll be focusing on RF-DYNAM Pro equivalent load. So this allows us to run a multimodal response spectrum analysis with the generation of equivalent static forces. And again, we'll be focusing on this per the ASCE 7 for today. So we might be asking ourselves, well, why can't we just run an equivalent lateral force procedure, and how does this differ from a response spectrum analysis? The equivalent lateral force procedure is covered in section 12.8 of the standard, and this really is a simplification of our seismic considerations as a static analysis. So we're applying these point loads and these point moments to our diaphragms. And this is fine for symmetric structures with minimal torsion, no irregularities, no discontinuities. So all in all, it's really for short, symmetric, regular buildings. And all too often we find ourselves outside of this range. And instead of running this simplified method, this is where we would turn to a modal response spectrum analysis. And this is covered in section 12.9 of the standard. So this takes into seismic considerations as a true dynamic analysis. We run our modal analysis to determine the mode shapes and modal mass participations for different frequencies of our structure. So this really can be considered with buildings with reentrant corners, irregularities in floor plans, discontinuities, maybe where we have off-center floors, where our center of mass is not near the center of rigidity. And essentially, this can be used for any type of structure. So perhaps you don't even have a building at all, but some type of specialty structure. Well, with a response spectrum analysis, you can consider seismic with all different types of geometry. So with that said, we will jump into our first example today within RFEM. So for the sake of time, I went ahead and I modeled our concrete structure here in our main program RFEM. So we can see over on the left-hand side is our project navigator. And because our model is already available to us here, we can view all of our input data over on the left-hand side. So for example, I can view all of my materials, and in this particular case, we're just using concrete 4000 PSI. All of my surfaces are available here that I can view for the different walls and slab elements. We also have some columns and beams modeled in. We can view those available cross sections here and so on. So what RFEM also allows me to do is to load the structure. So within my drop-down box at the top, I have a few different load cases. I have a dead load, which is just simple surface loads applied at each level. Same concept for the live load. We can see those apply to the structure here. And finally, I have a third load case, which is snow load applied only to the roof. So if I was interested in running a full static analysis with these loads, I would do so within RFEM. But instead, we want to immediately move to a dynamic analysis. And this is where we want to utilize our add-on module. So over on the left-hand side, you can see in the Project Navigator our long list of add-on modules. This is why we have the concept just pay for what you use. So for example, if you particularly don't run a lot of dynamic analysis for your projects, and you would never purchase the dynamic modules. So it just keeps the software catered for your individual design needs. So we can access RF-DYNAM Pro either here or within our drop-down box at the top under add-on modules. You can see the dynamic option in RF-DYNAM Pro. So an add-on module within RFEM, nothing more than a simple dialog box. And here we have all four of the dynamic modules that I mentioned within the PowerPoint. Now you'll notice that natural vibrations is immediately checked because, as I mentioned, this is a prerequisite to the rest of our dynamic modules. We also can activate the mass combinations, which brings up a new tab at the top. So all we need to do is just simply work from left to right with these tabs. So we move into the mass cases. Our first mass case is going to be dead. What we can do is to directly import the loads from RFEM. So all those surface loads I had applied at every level, I can import in from the load case dead. Now I do want to uncheck from self-weight of structure. I've already accounted for it in my load case back in RFEM. So if I leave this checked on, I'm accounting for it twice. And we can manually define additional masses, and I'll actually do this a little bit later on, but for right now we'll leave this empty. So we can make a copy of this mass case, and we will rename this to live and import in the live load case from RFEM. And we make a third copy here, and we rename this one snow, and we import the load case snow. So once we have completed our different mass cases here, moving on to mass combinations, we need to combine these together. And referring to the code, section 12.7.2, the standard tells us that we need to include 100% of the dead load. As far as the live load, if the live load is being used for storage, then we'd want to include 25% of the live load as well. Now, for my particular case, let's say this is some type of office building, and we're really not using this live load for storage. So I can leave this mass case over here on the left to not use it. And for snow load, we want to include 20% of snow load when our magnitude is greater than 30 psf. And in our case, we have 35 psf. So what we can do here is just to simply change the factor out in front to 0.2 to account for 20%. So we can give this mass case a name if we'd like to. We'll call this one dead plus 0.2 snow. And finally, we have our natural vibration case tab. So the lowest eigenvalues to calculate here is by default set to 4. That's a fairly low number, but for our first calculation today, let's just go ahead and go with 4. The scaling of the mode shapes, we have a few different options here. Now the default is just to take the square root sum of the squares. There are these different options, which I would encourage you to access the help manual down in the lower left-hand corner here for the dynamic modules that will give you a little bit more theory on these different scaling and mode shapes and to determine if they would be better for your design project. The calculation parameters, we want to choose here the mass combination that we had just created. As far as the acting masses, this is controlled by the type of mass matrix. So by default, the diagonal matrix with only translational degrees of freedom is selected here. So our masses are only going to act in the global X, Y, and Z, which we can see those global axes back in RFEM. The second option here, diagonal matrix, you can see will include both translational and torsional degrees of freedom. So now we're including masses about those axes. So several different options here. We'll just go with the first default. Now, similar to what we had just mentioned with the type of mass matrix, as well as the method for solving the eigenvalue problem, the different calculation types, you want to refer to the help manual to give you a little bit more insight on the theory behind each one of these. For today, we'll utilize the Langko solver, which is an iterative method to determine the lowest eigenvalues and corresponding mode shapes of large models. So essentially this allows us to determine a quick convergence. It'll run a little bit quicker than, let's say, something like the root of the characteristic polynomial, which will determine all eigenvalues and the corresponding mode shapes. As far as the stiffness modifications, we're going to leave this as no stiffness modifications for now, but keep this in mind because we're going to visit this much later when we discuss P delta. So all I need to do is click OK and calculate. The program's meshing it in the background in RFEM. We're running through our 4 different eigenvalues and we're immediately thrown back into RFEM. Now I'm technically still within this add-on module RF-DYNAM Pro. We can now see this within our drop-down box here. I think the most relevant information for these results will be related to table 5 here, dynamic analysis, and we can immediately jump to the effective modal mass factors. So here I can actually cycle through my 4 different mode shapes just to view what those essentially look like on my structure. But most importantly, we want to take a look at the last row in this table because this gives us our mass participation. So you'll see in the X we have 81.6% mass participation, in the Y 76, and in the Z we only have 2%. Well, this is actually a problem because section 12.911 in the standard tells us that we have to have a minimum of 90% mass participation of the actual mass in each orthogonal horizontal direction. So you can see that in my X and Y directions, I'm not meeting that 90%. Now, as far as the Z direction, today I'm really going to focus on excitations in only the lateral directions, but if vertical seismic is also something that you're concerned with, then you probably want to make sure that you have adequate mass participation in the vertical direction as well. So the question might be, okay, well, how do we get to this 90%? The easiest solution for this is just to simply solve from our eigenvalues. I've only solved for 4 here, so likely if we solve for something more like 10, we'll easily reach that 90%. Now, the other suggestion is that sometimes we have models where we are solving for 100 eigenvalues and we still can't reach that 90%. And this might be the scenario where we need to rearrange our mass. And what I mean by that for today, we can show a short little example of that, is if we take a look at our structure, we have this pretty large slab at the base here for our foundation, and currently we're considering it in a natural vibration analysis, but we could argue that all of this mass is really just being fed into the support, and it's not really contributing to the natural behavior of our structure. So maybe we completely deactivate this mass. Now, in a similar sense, if we look at all of our wall elements on the first level here, we might also argue that a lot of this mass is just being fed directly into the supports, and we're not getting as much mass participation as we'd hope for these wall elements as well. So what we can do with these walls is to actually deactivate them as well, and instead apply their mass at the top of the wall elements as line masses instead. So how exactly can we do this? Well, under the Views tab, and remember I'm back in RFEM here, I'm just going to activate my surfaces by material. So all that I've done here is I've just deactivated my columns and my beams. So only my surfaces are available with this graphic view. So I can select all of my wall elements on the first level, and I can create a visibility by the selected objects. So after all these elements are highlighted, I can right click and I can choose this option, center of gravity and info. What this is going to do is it's going to tell me the total weight of all of my elements selected here, which is 261,000 pounds. So somehow we want to redistribute this total weight here at the top of our walls instead as a line mass. So what we can do is to jump back into RF-DYNAM Pro, which we can access within our project navigator over on the left. What I'm going to do is to go to the mass cases, and I'm going to create a copy of my dead load mass case, and I'm going to rename it here to deactivate. And under the details option, this is where I have the ability to neglect masses. And I go into my special details. I have 4 different tabs at the top, including surfaces. So I can graphically select all of these wall elements that I have this visibility turned to back in RFEM, which includes 6 through 15 for my surfaces. Now I also, remember, want to select this slab at the bottom. So I could change around my viewports, but rather I can just simply type in surface number 1 in addition to this. And now you can see that bottom surface is highlighted as well. And we want to neglect these masses in the X, Y, and Z directions. So I click OK, and I'm brought back into my mass cases tab here. This is where we want to manually define additional masses on lines. I have a new tab up at the top. So all I need to do here is I can graphically select every line at the top of these wall elements, and I will exclude these interior walls though. So I have every line element selected on the exterior. Now I know the total length of the exterior of my building here around these walls is 215 feet. So I click OK, and what I can do is take that 261,000 pounds divided by the 215 feet to get a line mass of 1,215.11 pounds per foot. So now you can see the 261,000 pounds is represented in the sum here, so we're just redistributing that mass a little bit further away from the support to hopefully get more mass participation. As far as the mass combinations, we want to create a copy of our previous mass combination, and we're going to rename this one. All we're going to do is to swap out that dead load mass case. I'm going to instead bring over this dead load with the deactivate 100% plus 20% of my snow. So now for my natural vibration case, let's maybe solve as well for some additional eigenvalues. And by the way, as I mentioned, this is probably the first step that you want to take before you're redistributing masses. I just want to show both options in one step here with our example today. So we'll solve for 10 eigenvalues this time. Under the calculation parameters, we do need to choose our second mass combination here. So now we can click OK and calculate. So the program meshes the RFEM model in the background. It'll take just a split second longer because now we're going to calculate a few more mode shapes for a total of 10. So once the program's done, it brings us back into RFEM here. We can cancel out our visibility mode, and now we have the 10 different mode shapes available to us here within our dropdown, so we can view exactly what those look like graphically. Now, of course, what's most interesting is the effective modal mass factor table here. And at the very bottom, I can now see that I have 91% in the X direction for the mass participation, 93% in the Y direction, and 41% in the Z. So you can see what a significant difference those changes made with our total mass participation, and now we're meeting the 90% required by the standard. We might be interested in viewing what are our dominant modes. So we can take a look at mode shape number 1 here, and we see that this is our dominant mode in the Y direction, where most of the mass from the structure is contributing to this mode shape. We can take a look at mode shape number 2. This would be our dominant mode in the X direction. Now, this is in comparison to, let's take a look at mode shape 3 here, where we really have no mass participation, and this is really called a local mode. We just have something happening up here at the top of the structure, so you can see mass participation in the X and the Y is 0. So this mode shape really is not of much interest to us. Under the natural frequencies tab, this is where we can view the angular frequency, the natural period of our structure for these different modes. So now that we have determined here our natural behavior of our structure under the applied mass cases and mass combinations, we want to move into a response spectrum analysis. So under the data tab, we're going to go back into RF-DYNAM Pro. And this is where we're going to activate the response spectrum analysis with the generation of equivalent loads with our second dynamic add-on module, RF-DYNAM Pro equivalent loads. Now, everything remains the same for my natural vibration case. I didn't lose any of this data. It's still available to me. All that I've done is added a couple tabs here for my response spectrum analysis. And what we want to do first is to select our drop-down box here, and you can see the ASCE 7 2016. Now, we also have available the NBC 2015, as well as many other international standards. So moving forward with the ASCE 7, over on the left, we have some available data that we need to input into the program in order to correctly generate the response spectra for our project today. The first would be the site class, and with the site class, we've determined that with this particular concrete building, we have site class C. We also need to input in here the map spectral response acceleration for short periods, SFS, as well as for a period of 1 second. So what we can do is refer back to the ASCE 7 for this information, but instead, I actually want to refer you guys to our website here, and I actually will move this over. So if you go to our website at dlubal.com, under solutions, we have the option here for the snow, wind, and seismic zoning maps. And what we've done is we have integrated Google Maps technology along with the ASCE 7 maps and tables for snow, wind, and seismic loads. So how this is extremely beneficial is that all we need to do here is just to type in the location of our project. So for example, maybe this project today is located in Denver, Colorado. So we type in Denver, Colorado, and the map populates. We can hold down our control key to zoom in here. And we want to select seismic from our options up at the top. So now you can see with the seismic and this parameter drop-down box, we can choose S sub S. So this is the information directly from the ASCE 7 standard, and the S sub S is 25% of G. Same thing with S sub 1 that we'll eventually need. And we see that once this is populated, when we choose it from our drop-down box, we get 6% of G shown over here on the left-hand side. A few more parameters are available. The other important one will be the long period, which if we select this one, we can see that the long period is 4 seconds. So extremely beneficial if we just don't want to manually flip through those maps within the code. And the ability to go on our website and check this out for yourself is available. And we give you, a handful of trial clicks. But if you plan on heavily utilizing this feature, then you would want to purchase a GeoZone tool package within our web shop. So just something that's a little bit more user-friendly. So going back to the model here, what we can do is to type in the S sub S parameter that we just determined from the GeoZone tool. The S sub 1 will be 6% of G. And then all the rest of these parameters are calculated automatically within the program, but we do need to put in here the long period transition period of 4 seconds, which is already the default setting. So you can see our mapped response spectra down here at the bottom. We also have this information available to us in our table tab where we can export out to Microsoft Excel, for example. If you do choose user define, you have the ability to import in from Microsoft Excel as well. So moving on finally to the dynamic load case here, you'll notice that the only option available to me is the equivalent static force analysis. This is because I've only activated this dynamic module. All the rest of my options here are available with our other dynamic modules, more so to do with time history, for example. We do need to assign a natural vibration case. So we've only solved for one natural vibration case, so that's all that's available to us within our drop-down box here. Under the equivalent force analysis, we need to tell the program in which directions do we want to excite the structure. And for today, I'm only concerned in X and Y directions. If I was concerned with vertical seismic, then of course we'd want to activate Z as well. We also have accidental torsion here. So accidental torsion comes from section 12842 of the standard. And the code tells us that when diaphragms are not flexible, we have to account for assumed displacements of the center of mass. And how we do this is we set 5% of the structure's dimension perpendicular to the direction of the applied forces. So this is actually fairly easy to use. When we view eccentricity in the X, and we compare this to our global X axis here back in RFEM, this is the long distance, or long dimension of our structure. So 5% of that would be 47 inches. Now, in a similar manner, we have eccentricity in the Y. When we compare that in the Y direction here, it's the short direction of my structure. So this would be 5% is 24 inches. Now the program is smart enough to know that it should multiply the forces in the X direction times eccentricity in the Y. It will multiply the forces in the Y times eccentricity in the X to create that torsional moment. Combination of modal responses. We have two different options here, the SRSS and the CQC rule. So for this, I'm going to go back to the PowerPoint here. So here we have a whole set of equations. Now, each line item here represents an excitation direction. So we have excitation in the X direction, excitation in the Y, and excitation in the Z. And we're going to generate these equivalent forces, which are available to us on the left-hand side. And these are in X, Y, and Z directions as well. Now, over on the right-hand side, we have some additional variables, such as the participation factor. We have our mode shapes available to us here. S sub A would be the acceleration from the ASCE7 response spectra as a function of the building period. And then we have over on the right our masses. So we have all of these different mode shapes, and in our project today, we have 10 different mode shapes. So the question is, well, how do we combine all these different mode shapes for each excitation direction? And this is where we have one of two options. The first is the square root sum of the squares. And fairly simple formula here, you can see we're just going to square each modal response, add them together, and take the square root. The second option that we have is the complete quadratic combination, or the CQC rule. You'll notice that the equation for this is a little bit more complicated, which does include the correlation coefficient epsilon. Now, a huge difference here is that epsilon contains a damping factor. So we see that within this equation shown here. So with the CQC rule, we can consider damping as opposed to the SRSS, which we cannot. So going back to RFEM here, we want to consider the CQC combination. Now we have a damping tab available to us at the top. We can assign the signed results using the dominant mode. So within the PowerPoint, you just saw that in either scenario, I'm taking the square root of the result. So inevitably, we're going to lose that signage. Well, the program has the ability then to take that signage back in from the dominant modes, and we can see within the X and Y directions, we can leave this to let the program automatically determine what the dominant mode is, or we can manually assign it from the 10 mode shapes that we've solved for. We do want to generate the load cases. So the program is going to export out all of these equivalent loads for each mode shape as a separate load case. So I think it'll be interesting to see graphically how this looks on our structure. Now, furthermore, we want to create a result combination with our modal combination, and this is per the CQC rule. So essentially, we're going to see two result combinations, one in the X and one in the Y, because we've combined all the modal responses into a single result combination in each orthogonal direction. Now, furthermore, we have the combination of directional components. And for this, we refer to section 12.5 of the standard, which gives some guidance on the direction of loading. We have forces in the X and we have forces in the Y. So how do we combine these? Well, for seismic design category B, the code tells us that essentially we can consider both of them separately and just look at our results of our structure for each one individually. But there are other scenarios where we want to consider the 130 rule, where we apply 100% of the X and 30% of the Y, and vice versa, 100% of the Y, 30% of the X. So we should have a total of two result combinations here utilizing that 130 rule. Okay, so the final thing I want to just do is under the Details tab, the program limits here. If we exceed 5,000 equivalent loads on the generated FE mesh, the program won't display it to us. But I do want to show you that today, so I'm going to increase this value to 100,000, and we click OK and calculate. So the program needs to determine the natural vibration case, and in our particular scenario, it did already determine that. Then we move on to the dynamic load case with the response spectra. So we're running through those 10 different mode shapes, and then we want to, and actually I just remembered something. I actually need to show you guys a couple more tabs here. So let me jump back to DYNAM Pro. I forgot about damping. So jumping back to DYNAM Pro, let's try this again. The damping, we want to consider damping here before we export out those equivalent loads. So you can see within the damping tab, because we are combining according to the CQC rule, we have either Rayleigh damping or Leer's damping. Just to let you know that for the equivalent loads, it will convert Rayleigh damping to Leer's damping in the background. So if you prefer to put in an alpha and beta coefficient for damping, just know that essentially it's converted to Leer's damping anyway. Us as engineers, we're probably a little bit more familiar with damping. For Leer's, for example, concrete structure might be something like 5% damping. We also have the ability to set Leer's damping separately for each frequency or each mode shape of our structure, which you can see with this option over here on the right. Today we're just sticking with the 5%, and we do need to visit here our last tab before running those equivalent loads calculation. So you'll notice we did already solve for the natural vibration case, which we saw with the 90% rule that we needed to adhere by. And here are my 10 different mode shapes. We also give the mass participation directly within this table as well. What the program gives you the ability to do is to deselect modes that really are not much interest to us. So for example, I can deselect modes that are less than 3% mass participation. How this helps me is that you'll notice that I now have 3 modes here that are unselected, yet I'm still meeting that 90% mass participation. How that's a huge advantage is you can imagine with 100 different mode shapes, a lot of them may be irrelevant, so this will really slim down our calculation. So the program can automatically deselect those, but we still want to make sure that we meet the 90%. Okay, so now we are finally ready to run our calculation here with the equivalent load. So as I mentioned, the program already ran the natural vibration case. we're just going to move on to the dynamic load case and apply the response spectra per the ASCE 7. So again, we're brought back into RFEM, and as we saw before, here is our natural vibration case that we've solved for previously, but we now also have a dynamic load case. And within this dynamic load case, if we look at these tables here, we have all of our different mode shapes that we've solved for. Now remember, I slimmed this down to 7 different mode shapes now. We have every single FE mesh point available within this table from our structure here, and we have a force in the X, the Y, and Z direction, as well as a moment applied for accidental torsion. So that's what's happening here for the dynamic load case for each mode shape. Now, it might be a little bit easier to understand if we take a look at our load cases and combinations. So remember that I previously had dead load, live load, snow load as my load cases. Pretty self-explanatory. But what the program has done now is it has exported all of those equivalent loads for each mode shape as load cases back in RFEM. So you'll see here that for load case number 4, I now have my mode shape 1 for my excitation in the X direction with positive torsion. My next load case, exact same thing, mode shape 1 in the X direction for negative torsion. Then we take a look at the third one. We have excitation in the Y direction for positive negative torsion. We go through all of these to essentially determine the equivalent loads for each mode shape. So you can imagine that it makes sense that we need to somehow combine all of these different mode shapes into a single result combination. And this is why we've done so under the Result Combinations tab. The program has taken all of these mode shapes, which I can expand this column here. It has combined them here for the X direction for both positive and negative torsion, and we combine them according to the CQC rule. So this information here was brought in from the dynamic module. We're also going to sign it according to the dominant mode, which the program has determined. Now, in the Y direction, exact same concept here. We're going to take all of our mode shapes with excitation in the Y direction here, and we're going to combine them according to the CQC so that we just get a single result combination here for excitation in the Y direction, considering all relevant modes. Then also, as I mentioned, we have our 130 rule. So we have 100% of this X load acting and 30% of the Y, and then our second result combination here is 30% in the X and 100% in the Y. So jumping back into RFEM, if I take a look at one of these individual load cases here, I can display my load. So this is what the setting that I changed under the Details tab previously, just so that we can view this. And I know it's a little bit overwhelming because this is all of these forces being applied to every single FE mesh point. Now you'll notice that my walls and my slab are excluded here because if you remember, I excluded them entirely from my mass case. So that's why we're not seeing any loads in particularly acting on these surfaces down at the bottom. If I turn this model around and I zoom in here to maybe one of the columns, it'll make a little bit more sense. We have a single FE mesh node here, and then this is where we are applying our loads in the X, Y, and Z direction. We also have a positive moment acting here for accidental torsion. If I take a look at the next load case, we just reverse the moment. So that's what's going on for all of these individual load cases. Now, we'd like to go ahead and solve the model here. So all that we've done with that dynamic module is to export these loads back into RFEM so that we can now run a so-called kind of static analysis. So how we can do this now is go to Calculate, Calculate All. And for the sake of time, I have already solved this for all my different load cases and all my result combinations, and we're now presented with our results in RFEM. So maybe what I jump to here is my result combination with excitation in the X direction. And we can view the global deformations here. And most of our deformations in the x direction, which makes sense because this is where excitation is taking place. But in addition to the global deformations, well, under my results tab here in the project navigator, I can view my internal forces for my members. So for example, if I want to take a look at my columns here, and we can focus in on maybe these exterior columns, we can view the results diagrams for my axial loads. We can take a look at shear forces in both the strong and weak axis direction. We can view bending moments for both the beams and the columns. And this is based on just those seismic forces. In a similar manner, what we can do is to activate our surfaces results to us here in the form of contours. So with our surfaces, and maybe I highlight our slab down here at the bottom and I create a visibility by the selected objects, what we can view is maybe our bending moment along the local x-axis. We can view bending moment along the local y. We can view shear forces, normal forces, and so on. So this is all available to us despite any of the result combinations that we're looking at. So here's my excitations in the y direction now because I changed my result combination up here. Of course, we can view the 130 rule as well. So after we solve for all of these different seismic forces and how they're affecting our structure, what we want to discuss now is called the base shear. So let me cancel out this visibility and let's turn off the surfaces here and let's jump to one of these load cases of one of our dominant modes. So with the dominant modes, I can go to my dynamic tables here and I choose my dynamic load case. At the bottom of these tables, if I scroll all the way down, I get a summation here. And actually, I want to jump to mode shape number 1. And what this will show us is the base shear for the x and the y directions. And remember though that this is the base shear for only this particular mode shape. Now, you do need to take this number, by the way, and divide it by 2. And the reason why is because we are accounting for both positive and negative accidental torsion here. So your true base shear at the bottom of the structure in this table is this number divided by 2. So this is extremely helpful for these individual mode shapes that we can just access this table. But the question is that we're probably more so interested in our base shear for one of our result combinations instead. And that's after combining all of these mode shapes with the CQC rule, we want to look at result combination 1 here with excitation in the X. So we want to know what is the base shear and the story shear for our structure. And this isn't readily available in tables. So how can we access this information? Well, what I'm going to do is I'm going to hold down my control key here to select a single column stack within my building. If I continue to hold down my control key here, what I can do is to copy and paste this column stack here, and it asks me to clear my results. That's fine. So we've just made a single copy of this column over here on the right. What I'm going to do is to highlight all of these columns, right click, and under member, I want to edit. We're going to change the member type to what's called a result beam. Now, a result beam does not add any stiffness or any modifications to our structure. All that we're doing here is we're going to sum up all of the results from the rest of our structure and present it to you in a format of a member element instead. So you'll notice I won't even support this result beam here because we don't need to, because it's not a part of the analysis. We do assign some cross section. It doesn't matter. We'll just use one of the ones we already have defined here. We go into the edit member type details, and this is where we can choose from the listed objects. Now the default is set to all, and this is fine for today because I want to sum up all my surfaces. We don't have any solids, but it doesn't matter. We can leave this as all and all my members, and I want to present all of these results in a beam type format or a column type format over here with my result beam. So I click OK, I click OK. But what I need to do is I first need to go back to RF-DYNAM Pro, and I have to rerun this calculation. So because I've created that result beam, it cleared my results. We need to run back through initially the natural vibration case, which we can see here denoted within this dialog box. Then the program moves on to the dynamic load case. So we're exporting out all of those different equivalent loads from each relevant mode shape. So once the program finishes doing that, remember that I haven't actually solved for these loads within RFEM, but now all my load cases are available to me as well as my result combination. So we're just going to run this single result combination here for excitation in the X direction. The program's submeshing it in the background. Now remember, this column has absolutely nothing to do with the analysis, so it's not contributing any stiffness. Rather, we're just taking all of those mode shapes which are applied in the X direction and combining them per the CQC rule for this result combination. So eventually, the program will present to us our results here. Now, after the results are available, what I'd like to do is to activate here my Members tab. And what I'm interested in is the shear force for my result beams here in the local Y direction. So now for my excitations in the global X direction, I'm viewing the shear forces on my result beam, which is summing up what's happening with this entire structure. So it's summing up the shear forces from my foundation all the way up to the top of the structure. So when we zoom in here, we can take a look at these particular shear forces, and down at the bottom our shear force would be 679, our base shear, minus the 704.9. Now this is a little bit counterintuitive, but remember we deactivated all these masses and we applied line masses instead, so it makes sense that our story shear at the first level is actually higher than our base shear. So our story shear at the first level would be the 704.94 minus the 593. We do so at the second floor at the 593 minus the 415, and so on. So that's the individual story shear. Clear up to the top of 177.46 is the story shear for our top level. So with this information, I want to go back to the PowerPoint here to discuss base shear considerations. Section 12941 of the standard addresses scaling of our forces. And the code tells us that we need to determine the base shear in two orthogonal horizontal directions. And with our case today, that's X and Y. From here, the code has the variable V sub t. And V sub t is what is the RFEM's modal base shear from the combined response, again, according to the CQC rule, from the result beam. So I just showed you how to determine that base shear from the result beam. Now we compare that to the shear within the standard, which is calculated from the equivalent lateral force procedure from section 12.8. So you can manually calculate this value. Now, when our modal base shear from RFEM is less than 100% of our equivalent lateral force procedure shear, then we need to scale our base shear by a factor, and that factor is just simply V over V sub t. So if you are not meeting this criteria, then you can go ahead and scale your shear forces within RFEM in RF-DYNAM Pro, and we can do so with these factor settings here. So going back into RF-DYNAM Pro under my data tab, I can access that here again. And I just want to show you guys under dynamic load case equivalent force analysis, this is where maybe we want to put in a factor of whatever that comes out to be. So that is the ability here to set that if we aren't meeting the modal base shear. The other consideration that we want to discuss is drift. And with story drift determination, this comes from section 12.8.6. And the code tells us that we need to determine some different deflection location points. These are set at the center of mass for each different story. Now, if the center of mass does not coincide at the same location for every level, then we have the ability to project the center of mass at the top of the story onto the center of mass, or sorry, down onto the bottom of the story. So that way we have a straight line passing through our entire structure. Now for seismic design category C through F, or if we have torsional irregularity, the standard tells us that we must also consider edges. Well, this is fairly easy to determine within RFEM, which I'll show you guys in just a minute. But just keep in mind that deflection is not purely the information that we pull from the program, but rather it comes from equation 12.8-15, where we multiply this deflection times the deflection amplification factor C sub D, and we divide by the importance factor I sub E. So this is the true deflection according to the ASCE 7. Then the calculated drift for each floor is just simply this deflection from the equation above from the top floor minus the deflection from the bottom floor. So section 12.942, also in a similar manner, similar to the base shear, tells us that we need to scale the drifts when V sub T, which is the modal base shear from our result beam, is less than C sub S, which is the seismic response coefficient, times the effective weight. In other words, this is known as V from the equivalent lateral force procedure, exact same situation that we just saw with base shear. So then we would want to scale our drifts by this V over V sub T ratio here. So back in RFEM, what we can do with the center of mass is that for a particular story, you can select the slab and all elements that are framing into it, and we can right click, and under center of gravity and info, we have the ability here to create a new node at the center of gravity. So the program will actually place a node in there. Now you would want to double click on that node and move it up to the elevation of our top story here, but then we would take that node and project it down through all of our different stories. And for the sake of time here, I went ahead and did that with an already saved model. And you'll notice here that I created my center of node up at the, or center of mass at the top story, and I projected down through each level. What I also did is I selected all my nodes at the edge points here. And under the Views tab, I created a user-defined view with only these nodes selected that I'm interested in for drift. So once we run our calculation, we can view the deflection here for our result combination in the X direction, for example. So under the results, we can view deflection in the X direction. We can zoom in here to an edge point, let's say, and the deflection here for our top story is given as 0.207. Well, the story below it is 0.161, but don't forget that we do need to multiply by the C sub D factor, divide by the importance factor, which is what the code tells us. So an easy way to pull all this information of only the relevant nodes we're interested in is to create this user-defined view. I can highlight all of my elements here, so you can see they're selected with red. Now in my tables, I can jump to my table 4.2, which shows my deformations of my nodes. And we have this nice tool that says show selected objects only. So now within this table, it will only show me my nodes that I graphically have selected here rather than every single node within the entire building. And I can export this deflection information directly to Microsoft Excel. I can run the deflection equation per the ASCE 7 if I need to scale drifts and so on. So that's how we can efficiently calculate what the drift is for any type of structure within RFEM. Okay, so the final topic to discuss here would be P-delta considerations. So P-delta effects come from section 12.8.7, and it refers to this equation over on the right with theta. P-delta effects can be completely neglected when theta is less than 0.1. However, if we have the situation where theta is greater than 0.1 but less than theta max, which is also given within the standard over here on the right, then we need to multiply our displacements and our forces by 1 over 1 minus theta. So this is how we can easily consider P-delta effects if we are not meeting this criteria here. It's just kind of a simple conservative way to export out, I don't know, displacements and forces and multiply by this factor. Now, keep in mind, if theta is greater than theta max, the code tells us that we do need to completely redesign the structure because it's not safe. So this might be fine for a simple application, but we maybe are rather interested in how we can include p delta directly within the analysis. Well, when we take a look at p delta, we actually cannot iterate p delta calculations for second order theory within dynamic analysis. It just is not applicable. So what we do is we linearize this with what's called the geometric stiffness matrix based on axial loads only. Now there are two assumptions with this type of linearization. One is that vertical loads do not change due to horizontal effects, and the second is that deformations are small when we compare this to the overall dimensions of our structure. So as far as the geometric stiffness matrix, which is denoted by K sub G, this tells us that essentially tensile axial forces increase the bending stiffness of a member. Now, in turn, a compressive axial force will reduce the bending stiffness. Now, a very simple application on how this can be applied is if we think of a cable. When a cable is in tension, then it certainly has an increase in bending stiffness. But when we apply a compression force to a cable element, it's really completely useless. So we have reduced its bending stiffness. And this K sub G reflects this stress stiffening effect. Over on the right-hand side here, we have a set of equations with just 2 degrees of freedom to kind of show you what this means. Now, over on the left, we have our force. Over on the right, we have our geometric stiffness matrix, K sub G, and we have this multiplied by the displacements. Well, you'll notice that the geometric stiffness matrix is only dependent on 2 variables, and that is the axial load within the member and the length of the member. It's not dependent on anything else. So here, to account for p delta, we can take the geometric stiffness matrix, we can add it to the elastic stiffness matrix K, which is what we've been using up until now, for a modified stiffness matrix K mod. So K mod is just simply K plus KG. So how do we do this within RFEM? Well, I'm going to go back to my load cases and combinations here. And we have yet to visit this load combinations tab. So referring back to the ASCE 7, section 236, there are some load combinations, of course, that we want to put together to account for both gravity loads and seismic. And in particular, my worst case scenario is equation 6. And what this includes, if we create a new load combination here, is 1.2 dead plus live plus 0.2 snow, and eventually we'll add in our earthquake as well. But for these gravity loads only, I change around my load factors here to reflect what the code tells us. So 1.2 dead plus live plus 0.2 snow. So now I have this existing load combination with only gravity forces or axial loads. I am going to go back into RF-DYNAM Pro, and if you remember way back when, under my natural vibration case, my first natural vibration case had no stiffness modifications. So we'll rename this no stiffness modifications. And I'm going to make a copy of this, and this time we want to rename this one geometric stiffness modifications. Everything remains the same here. The only thing that I'm going to do is I'm going to import in the axial forces from that load combination that I just created, load combination 1. So I'm bringing in all those axial forces from my gravity loads. Under my dynamic load case, well, we have our first dynamic load case here, which did not consider p delta. So we'll type in here, we'll just give it a description of no p delta. I make a copy of this one, and we will just take away the no here so that we know that this one is including p delta. The difference here is I need to choose my natural vibration case where I have now included this geometric stiffness modification. Everything else remains the same here. We're still relating the response spectrum analysis per the ASCE 7 to the X and Y directions, accidental eccentricity, and so on. But now I'm going to click OK and calculate. And I already have a saved model here, again, just for the sake of time. We'll jump to this model here where I've exported out all of my natural vibration cases as well as my dynamic load cases where I have and have not considered P delta. So now if I take a look here at all of my load cases, we have double the amount of load cases. Well, initially, all of my load cases, which we've already covered from my dynamic load case not considering P delta, are shown here. The calculation parameters are set to a geometrically linear analysis. So with a P delta analysis, this is a two-step process. We first took care of it to modify the geometric stiffness matrix when we exported those equivalent loads back out to RFEM. But we need to actually run a second order analysis within RFEM as well. So what I'm going to do is to take all of my mode shapes from my second dynamic load case here. So again, these are the ones where I have considered that geometric stiffness matrix. I'm going to change this to second order analysis considering P delta effects. So I've already done this, but just keep this in mind. If you were following along, you would need to change this to second order. We also want to activate this extra options here. And now under extra options, we import in the stiffness modifications from the load combination considering those gravity loads. So again, load combination 1 with dead load, live load, and snow load. So we run the calculation, and remember, we still have the scenario where we need to combine all of those different load cases with the CQC rule. So that's why we have 4 sets of result combinations here, not considering P delta, and we have 4 considering P delta. So nothing to do further here. The program's simply going to combine all of those individual load cases with the CQC. So once we run our analysis, we can actually compare, let's say, the results from the X direction excitation. And maybe we take a look at internal forces, deflections for all of our elements here under the results tab. And we compare it to the exact same excitation direction, but without P delta considered, and see how that varies. Now, for my example today, really had no difference at all. And that's likely because my theta equation from the ASCE 7 is really, really small. So P delta did not make too much of an influence. But there are scenarios where P delta does need to be considered. So this is the effective way to do it within the actual calculation itself. Now, the last thing to do here is under my result combinations, we've created all of these seismic forces, but I have yet to combine them with my gravity loads. So we can do one last thing here to create an additional result combination just manually. And I'm going to take my load combination 1 that I'm running with a second order analysis. That's all my gravity loads. And I'm going to add in my 130 rule. That's considering P delta. But I want to take both of my 130 rules because I don't know which one provides a worst case scenario. And we can use this option here with the OR operator. Now, with the OR, I want to change my load combination up here for load combination 1 to permanent. These 2 result combinations are variable, so the program will determine what is the worst case scenario for my 130 rule and add that to my gravity only loads. So I can click OK, and actually the program doesn't even need to run a calculation with this result combination. And the reason why is because it just uses superposition here to add up those load combinations along with the result combination. So immediately we're presented here with our deflections, our internal forces. So this is the result combination then that we could take into additional add-on modules and design all of our reinforced concrete slabs or columns, for example, per the ACI or the CSA standard. So that's how we combine everything into a single result combination. Okay, so that concludes today's webinar. As I always say, I know that was quite a bit of information. You can always visit our website at dlubal.com to learn more about dynamic analysis or any of the capabilities that we have within RFEM. I always encourage everyone to follow us on our social media sites. For example, you heard me mention our YouTube channel. Well, this has all of the previously recorded webinars such as these that you can watch at your own convenience. Also give you more information on events and conferences that we'll be at, maybe some technical articles that we posted on our website. Our email at our Philadelphia office is info-us@dlubal.com, and our phone number is 267-702-2815. So if you have any questions about today's presentation or anything else, feel free to reach out to us here. Also, we will have many more upcoming webinars. You can register on our website at dlubal.com under support and learning and webinars. As most of you know today, though, I sent out a reminder email about a week or so before one of these will take place, and you can always register through there as well. Many of you are wanting PDH certificates for today, and that's great. Just to let you know that these will automatically be emailed to all participants within the next day or so. So no need to request those. They will be emailed to every participant who was here for the full presentation. So this is required by the states that you are available for the full webinar. So if you don't receive one of those, it's likely because you missed, a significant portion of the presentation. If any additional attendees watch this webinar today but did not individually register, you will need to request this at info-us@dlubal.com. So again, if you watch this with a colleague or as a group and you yourself did not individually register but you are wanting a PDH certificate, then please send us a request at info-us@dlubal.com, just letting us know that you were in attendance today along with your name. And as always, I want to thank everyone for attending today's presentation, and we hope to see you at the next one. Thank you.